the K-cat over Km. So the K-cat over Km value for the interaction between chymotrypsin and glycine is 1.3 times 10 to the minus 1. It's not very large. So the interaction between chymotrypsin and glycine is not great. And we start to look at other amino acids like valine, right? What's the K-cat over Km between chymotrypsin and valine? Well, now we have a K-cat over Km of 2.0. So that rate constant for the interaction between E, in this case chymotrypsin, and S, in this case valine, is higher. That means that V0 is higher, so the interaction proceeds forward more rapidly. So it's a stronger interaction. It's more specific for valine than it is for glycine because the K-cat over Km value is higher. We go on down here to phenylalanine. Well, now our rate constant is 100,000, right? 10 to the 5. So the interaction between phenylalanine and chymotrypsin is much higher than the interaction between valine and chymotrypsin. So chymotrypsin is more specific to phenylalanine than it is for valine. And so we use K-cat over Km to talk about the specificity of an enzyme. Now, how high can K-cat over Km go? Well, now we're simply just limited by the diffusion controlled rate, or the diffusion controlled rate of an encounter. What does this mean? Well, the interaction between E and S can't be any greater than the frequency at which E and S encounter each other in solution. So there is a limit to how high K-cat over K can go. You can imagine that you can have a kinetically perfect enzyme that as soon as it interacts with a substrate, right, it always immediately binds and catalyzes the reaction, and on we go. Other enzymes might take a couple of interactions, right, to bind with their substrate. So the best that we can hope for is that every time that there's an encounter, there's a binding event and catalysis occurs. And that ends up being somewhere in this neighborhood here of 10 to the 8 to 10 to the 9-ish. Okay, so superoxide dismutase is one of the most kinetically perfect enzymes that we know. It's got a K-cat over Km value of 7 times 10 to the 9. So the rate constant of the interaction between superoxide dismutase and a reactive oxygen species is very high. That means that they always bind, essentially, right? 99.99% of the time they bind and catalysis occurs. We look over here, acetylcholinesterase also has a very high K-cat over Km value. This is important. Acetylcholinesterase, we'll talk about when we look at membranes, is responsible for degrading acetylcholine in synaptic clefts. And this has to happen very rapidly in order to get the proper pattern of depolarization and repolarization of the synaptic membrane. Now on to enzyme inhibition. While Km cannot change, right? It's an intrinsic value to the enzyme. We can alter Km apparently, right? So we call this the apparent Km. Vmax similarly, we can change. Now we know we can change Vmax based on how much enzyme we have. Remember, Vmax equals K-cat times E total. So if we add more enzyme, we get a higher Vmax value. Okay, but we can also alter the Vmax value depending on the presence of an inhibitor. There are 3 different types of inhibition, right? So here we have obviously no inhibition, so the substrate just binds the enzyme. Competitive inhibition is when the inhibitor molecule resembles in some way structurally the substrate, and it competes for binding of the active site of the enzyme, so it's a competitive inhibitor. Uncompetitive and non-competitive inhibitors, though, are a little bit different. Okay? Uncompetitive inhibitors bind only the enzyme substrate complex. They don't bind the enzyme alone. So while competitive inhibitors necessarily bind only the enzyme and not the enzyme substrate complex, uncompetitive inhibitors bind only the enzyme substrate complex. And so the binding of the substrate and the inhibitor are linked in this way. And as we'll see, that's going to cause a change in the apparent Km value, but it's not going to change, as we'll see, the Vmax value. Non-competitive inhibitors don't bind anywhere near the active site, and in fact, the binding of the non-competitive inhibitor is completely independent of the binding of the substrate, right? What does this mean? This means that the enzyme is quite happy to bind the substrate or the inhibitor or both, and nothing changes. So the binding of the inhibitor and the substrate are independent. And in this way, okay, the Km value is not going to change, but we are going to change the Vmax value. And non-competitive inhibitor would be an example of an allosteric regulator. Okay, it regulates the enzyme allosteric. does something to slow it down without necessarily affecting how the enzyme binds the substrate. We can tell these apart kinetically. So here's an example of a competitive inhibitor, caffeine, right? So if you go to Bush campus in front of the Life Sciences building, or the new chemistry building, actually, there's a big statue of the caffeine molecule. I'm not sure why they put it there, but this is caffeine. The reason why caffeine is used as, to promote alertness, I guess, in terms of caffeine, is that it is a competitive inhibitor of the adenosine receptor. The adenosine receptor in the brain recognizes, obviously, adenosine, but specifically ADP. And ADP levels tend to build up throughout the day as we use up more and more energy. And these ADP levels begin to bind to these adenosine receptors, and they trigger, the cascade that leads to you feeling tired. Caffeine binds to the same receptor. Look, it looks very similar to adenosine there, or adenine. It looks very similar. It binds to the ADP receptor, and it blocks it from acting. Not only does it prevent ADP from binding, but it also helps to slow it down. Right? So let's look at, it helps to slow it down by preventing ADP from binding. All right, so let's look at a competitive inhibitor. We have this schematic here, okay? We have an enzyme, substrate, and inhibitor. The enzyme binds with the substrate to form the enzyme-substrate complex, or the enzyme binds with the inhibitor to form the enzyme-inhibitor complex. Now, here we have a Ki, and the Ki is just the Kd for the interaction between enzyme and inhibitor. So it's essentially just Kd between E and I. The smaller the Ki, the stronger the inhibitor binds. And the stronger the inhibitor binds, the more it's going to prevent the substrate from binding. So a small Ki inhibitor will have an outsized effect compared to a large Ki inhibitor. So let's examine what's going on here, right? So from enzyme inhibitor and substrate, we can either form the enzyme-substrate complex or the enzyme-inhibitor complex. So once you're in the enzyme-inhibitor complex, the substrate can outcompete the inhibitor for binding to form the enzyme-substrate complex. The effect of this triangle here is that we've effectively reduced, right, the amount of substrate that can bind at any given time to the enzyme, right? So we've effectively, what? We still have the same amount of enzyme. So remember, Vmax equals K cat times E total. So that hasn't changed. And we're not changing the amounts of any of these. We're just changing the rate at which they bind, okay? So Vmax remains the same, because E total is still the same in this case, right? But what happens to Km? Well, Km now increases. Why does Km increase? Well, now, notice, we can bind to the enzyme straight up, right? But some of the enzymes will be converted into enzyme inhibitor complex. And now the substrate has to outcompete the inhibitor. And depending on the Ki of this inhibitor, this might take a while, right? So it's going to take, or more substrate concentration. So in effect, what is happening is that it's going to require more substrate concentration to reach the same V naught that we would have in the absence of the inhibitor. And that results in an increase in the apparent Km value. Right, so here let's see, within the presence of no inhibitor, here's our Km all the way down here. It's not marked, but it's close to 0, right? So whatever you want to call it, the numbers aren't important. But now as we begin to add inhibitor, well, what's going to happen? Right? Well, now we have to add more substrate to reach that same V naught, 50%. Right? So the Km has increased. As we add more inhibitor, now it requires even more substrate to reach that same velocity. As we add more inhibitor, right, now we have to add even more substrate. Again, because now there's more inhibitor, right, more substrate is required to outcompete that inhibitor here, okay? Because a lot of it now, as we increase the inhibitor concentration, being converted into EI, where we have to wait for the substrate to be able to outcompete. But this can be overcome simply by just adding more and more substrate. So we can reach the same Vmax, right? We can still reach the same Vmax, it's just going to take more substrate to get there. So we have an apparent increase in Km. Now the actual Km, again, remember, is immutable, right? It's intrinsic to the enzyme. So we're not changing the Km of the enzyme, what we're changing is the apparent Km of the enzyme, Km apparent. Now, uncompetitive inhibitors reduce both Vmax and Km, right? Or the apparent Km. And how do they do this? Well, again, remember, uncompetitive inhibitors are only capable of binding the ES complex, not the enzyme first need a binding event between enzyme and substrate, right? This event, right, or this phenomenon where it can only bind the enzyme-substrate complex means that, again, the binding of the inhibitor and the substrate are linked. The inhibitor cannot bind without the substrate. And the effect that this has, right, ES now binds to the inhibitor, and we form the enzyme-substrate inhibitor complex. Whereas before, remember, in competitive inhibition, we could only have either EI or ES. Now we can only have ESI if it's being inhibited. Effectively, what we're doing then is removing some amount of ES complex so that it forms this unproductive ESI complex, right? So the ESI complex isn't doing anything, or at least not doing anything useful, okay? So the concentration of ES is now decreased. So if we look at this process then, right, binding of enzyme to substrate, well, what's going to happen now? If this concentration goes down, all right, what's going to happen to this process? Is it going to go faster or is it going to go slower? If we remove ES, right, so ignore all this right now, say that we're magically just reducing the concentration of ES. What's going to happen to this process right here? Will it increase in rate or decrease in rate, or no change in rate? Increase? Why do you think it will increase?
Because it's going to compensate for the reduction of ES.
Right, this is just an extension of Le Chatelier's principle. If we decrease the product, in this case ES, well now the rate of this reaction goes forward. Okay, so more substrate binds to enzyme. Okay, so the apparent rate here, or the apparent rate constant, increases. Right? Apparent rate constant increases. And what is that rate constant? Okay, remember, Km equals K minus 1 plus K2 over K1. The binding of enzyme to substrate is just K1, remember, from the Michaelis-Menten derivation. So if K1 increases, then Km necessarily decreases. And that's what we see here. The Km, or the apparent Km, for the interaction between enzyme and substrate goes down in the presence of an uncompetitive inhibitor. Now, because we're also reducing the effective amount of ES, right? Remember, the rate is determined by the concentration of ES. Okay, and because there will always be some amount of ESI present, this reduces the effective concentration not only of ES, but of E total, right? So we've effectively removed some of the enzyme that we added. And Vmax equals Kcat times E total. So Vmax decreases as well. So in the presence of an uncompetitive inhibitor, Vmax decreases because we're removing some enzyme by forming this enzyme-substrate inhibitor complex. And Km decreases because now, in order to compensate for that lower ES concentration, more S will bind to enzyme, right? And this pushes K1 up, which of course pushes Km down, right? So it takes less substrate to reach half of our Vmax, which we normally think would increase the overall rate of reaction, but Vmax that we can achieve has also been decreased. So while it takes less substrate to get to 1/2 of Vmax, 1/2 of Vmax is lower than it was in the absence of the inhibitor. So the overall effect is to slow down the rate of the reaction at any given substrate concentration. Non-competitive inhibitors are a little bit more complex to understand. Non-competitive inhibitors, again, bind independently of the interaction between substrate and enzyme. So we can get enzyme inhibitor complex, we can get enzyme substrate complex, or enzyme substrate inhibitor complex. Okay? Now, again, just like last time, because here we're forming an ESI complex, we're effectively reducing the concentration of E total. Right? We're removing some of that ES, which means, in fact, we're removing some of the enzyme that we added, so the Vmax, which again equals Kcat times E total, decreases. So we can see that here, the Vmax in the presence of a non-competitive inhibitor decreases. But the Km, or the apparent Km, doesn't change. The apparent Km remains the same. And the reason for this is that there is no relationship between the binding of the inhibitor and the binding of the substrate. So it has no effect on either K-1, K2, or K1. right? These will continue exactly the same as if the inhibitor weren't there. So the apparent Km remains the same while the Vmax decreases. So in this case, while it's more difficult to understand the schematic, it's easier to understand why the rate is always lower. The Km remains the same, so the amount that you need to reach half of Vmax is always the same, right? As opposed to an uncompetitive inhibitor where it is less, here it remains the same, but the Vmax that we can achieve, or the 1/2 Vmax that we achieve at that Km, is always going to be lower because we've reduced the Vmax by reducing the effective total concentration of enzyme. All right, so these are the three modes of enzyme inhibition, and we can tell them apart very easily using a double reciprocal plot. And we went over the Lange-Weaver-Burke plot, yes? Yeah. Okay, so we have three different types of inhibition, all of which affect key kinetic parameters in different ways, right? So the competitive inhibitors only increase Km, the uncompetitive inhibitors decrease both Vmax and Km, and non-competitive inhibitors only affect Vmax. So if we know that the y-intercept of a Lange-Weaver-Burke plot is 1/Vmax, and that the x-intercept is -1/Km, well, now it's very easy to tell them apart. Here, what's changing? Well, 1/Vmax remains the same, which means, of course, that Vmax is remaining the same, so Vmax is not being affected, whereas Km is, or -1/Km is changing, which means, of course, means that Km is changing. So here, in the presence of no inhibitor, what do we have? Well, we have this Vmax, or this 1/Vmax, and we have this -1/Km. Now, if the Km increases, what's going to happen to -1/Km? Well, it'll be closer to 0. Right? Of course, if we increase Km, that value, 1/Km, will be smaller, and it's negative, so it just means it moves closer to 0, and that's exactly what we see here. In competitive inhibition, we get this X pattern, where they intersect at the y-intercept, which is 1/Vmax, and in the presence of the competitive inhibitor, the x-intercept is closer to 0 because the Km has increased, right? Comparatively, if we look here at non-competitive inhibition, we see a very similar thing going on. Only now the x-intercepts at the x-intercept, right? Because Km is remaining the same in the presence of a non-competitive inhibitor. But remember, in non-competitive inhibitions, Vmax decreases. So, or 1/Vmax then should increase, right? So that's what we see here. 1/Vmax is increasing compared to the no inhibitor line, right? So it's very easy to tell these apart on a Lange-Weaver-Burke plot, especially when we're talking about non-competitive versus uncompetitive inhibition, where they're both changing or they're both decreasing the Vmax, but it can be a little bit more difficult to determine what the Km apparent is. Now, for uncompetitive inhibitors, because both Km is decreasing and Vmax is decreasing, what we get is an increase in 1/Vmax, right? If 1/Vmax or Vmax is lower, 1/Vmax will be larger. And we get a -1/Km that is farther away from 0. Remember, if Km now is decreasing, 1/Km will be larger, but it's negative, so it's just farther away from 0. And that's what we see. And recall that the slope here is Vmax/Km, or Km/Vmax, sorry. The slope here is Km/Vmax. As it happens in uncompetitive inhibitions, Km and Vmax are linked, right? So that the ratio between them always remains the same. And when the ratio between them remains the same, these slopes of these lines also are always the same. So in uncompetitive inhibition, not only do we see a change in both 1/Vmax and -1/Km, we also see that the slopes of these two lines are always equal. So they're parallel lines in the double reciprocal plot for uncompetitive inhibition. All right, so those are the three types of inhibition you should know. Those you should be able to distinguish between them. You should also be able to see a Lange-Weaver-Burke plot with actual numbers and determine what the Vmax is, what the Km is, what type of inhibition it is, the apparent Km, and all this, okay? All right, so now on to carbohydrates. That didn't take too long. We might have to skip proteoglycans in chapter 11, but after this, then we'll be all caught up and we can get involved. Right, so carbohydrates are the first type of fuel that we're really going to examine, right? So as we go forward in this semester, we're actually going to take, an in-depth look at most of metabolism, including carbohydrate metabolism, fatty acid metabolism, protein metabolism. Right, so we're going to start that chapter 15, but before we get there, it's important to introduce the different types of metabolites or molecules that are going to be taking part in these metabolic processes. So, sugars, saccharides, right, monosaccharides are the simplest carbohydrates. Now, carbohydrate is just exactly as it sounds, the hydrate of carbon. So 3 to 7 carbons in a chain, and at least 2 hydroxyl groups. Okay? So let's look at the simplest carbohydrates, which contain 3 carbons, and we see already that we have some variety here. Right? We have some variation. We have dihydroxyacetone, and we have glyceraldehyde. Let's start with dihydroxyacetone. Dihydroxyacetone is what we call a ketose. All sugars, all saccharides, and in OSE, so glucose, sucrose, fructose, maltose, mannose, galactose. All of these are sugars. They all end in O's. Okay? And what we see here is that we have a ketone group. So this is called a ketose. Right? All monosaccharides are going to have either a ketone group, as in dihydroxyacetone, or an aldehyde group, as we see in glyceraldehyde. Here we have D-glyceraldehyde and L-glyceraldehyde. These are both called aldoses. And the reason we have 2 variations is that we have a chiral center here. This carbon, carbon number 2, notice, is asymmetric. Okay, so it can exist in one of 2 mirrored forms. We call these D and L. This is the simplest sugar to be identified, and the D and L were named for the way that it rotates light in solution. Right? So if we have a solution of D-glyceraldehyde and you shine polarized light through that sample, it actually rotates that light a couple of degrees to the right. And the same is true for L-glyceraldehyde, only it turns that light to the left. D and L. From these 2 designations, D-glyceraldehyde and L-glyceraldehyde, we derive all of the D and L configurations for the more complex or longer sugars. So we can have D-glucose, L-glucose, D-mannose, L-mannose, and so on and so on. And these are named for their similarity to either D-glyceraldehyde or L-glyceraldehyde. So now we have our 2 classes of sugars, our ketoses and our aldoses. On top of this, we can have a multiple number of carbons. We can have 3 carbons, 4 carbons as in erythrose. We can have 5 carbons like in ribose, 6 carbons in glucose, or 7 carbons as in acetylheptulose. Right? These are called trioses, tetroses, pentoses, hexoses, and septoses, respectively. All right? And we can combine these words together. So if we're talking about glucose, we'll see the structure of that in just a second, we refer to that specifically as an aldohexose, because glucose is an aldose, but it's got 6 carbons, so it's both an aldose and a hexose, so we just merge the words together. Ribose would be, for example, a aldopentose. Okay, fructose is a ketohexose, right, and so on and so on. So we can classify sugars based on both. Do they have an aldehyde or ketone group? They must have one or the other, and how many carbons do they have? Now, carbohydrates can exist in many forms, okay, in many different isomeric forms specifically. Right, so what are isomers? Well, isomers can be broken down into 2 categories, right? Constitutional isomers and stereoisomers. Constitutional isomers are, for example, glyceraldehyde and dihydroxyacetone. They have the same number and type of atoms, so the same number of carbons, oxygens, and hydrogens, but they're linked together in a different way. Okay, so even though you write down the chemical formula on a balanced reaction and it looks the same, right? Same number of carbons, oxygens, and hydrogens, they have vastly different properties and do vastly different things. These are constitutional isomers. Somewhat more relevant for the discussion of saccharides or sugars are stereoisomers. From stereoisomers, things can get a little bit more complex, but also much more interesting. We can break stereoisomers down into 2 further subcategories, enantiomers and diastereoisomers. Enantiomers are easy. They are simply just complete mirror images of each other, okay, enantiomers. So an enantiomeric pair are just 2 mirror images of each other. But in order to be enantiomeric, there has to be at least 1 asymmetric carbon, or at least 1 chiral carbon. So in the case of dihydroxyacetone, the reason why we don't have a D or L dihydroxyacetone is because there is no mirror image of this that is not the same as what we started with, right? So here, this carbon is not asymmetric, it's bound to 2 hydrogens, right? Does everyone know how to tell if a carbon is asymmetric or not? Should we go over that? Does anybody want to go over that? No, okay, all right. So dihydroxyacetone, right, obviously is then non-symmetric. None of these carbons are asymmetric, so we can take the mirror image of it, but then we can just superimpose it right back on the original, right? So we just took the mirror image and ended up with the same thing. The same is not true for glyceraldehyde, right? If you take the mirror image of it, there's no way that you can superimpose the two back together so that you end up with the same thing. So they're non-superimposable mirror images of each other, D and L. Any D and L pair of sugars are an enantiomer. So D-glucose is simply the mirror image of L-glucose, right? And vice versa. D-mannose is the mirror image of L-mannose. And how do we take the mirror image? Well, here what we're looking at is what we call the Fisher projection. Is everyone familiar with the Fisher projection? Okay, so we look at the Fisher projection and we see, all right, which carbons are asymmetric. So in this case, right, carbon number 1 is not asymmetric, carbon number 2 is, and carbon number 3 is also not asymmetric. So we only have one chiral center. So in order to take the mirror image, we just flip the hydroxyl and the hydrogen to opposite sides. Now we've taken the mirror image. And these are now no longer superimposable. If we have, for example, 2 chiral centers, then we would have to flip both chiral centers to take the full mirror image of the molecule. We have 3 chiral centers or 4, we have to flip every single chiral center in order to take a full mirror image of the entire molecule. Diastereoisomers are stereoisomers that are not mirror images of each other, which is to say that they vary at at least 1 chiral center, but not all of them, right? Because remember, if they vary at all of them, if all of them are mirrored, then what we have are enantiomers. So if we have mirror images of only some of the chiral centers, what we have are diastereomeric pairs. For example, altrose and glucose, right? So if we look at glucose here, this is one that you should know off the top of your head. We have 6 carbons. It's got an aldehyde group, so again, it's an aldohexose. This carbon is not asymmetric, but this one is, this one is, this one is, and this one is. Carbon number 6 is also not asymmetric, okay? So we have 4 chiral carbons. If we look at that and compare that to altrose, is also an aldohexose, right? This is not asymmetric, this is not asymmetric, but these 4 in the middle are, okay? Well, now let's compare between the two. Well, this has been mirrored, this has been mirrored, but these 2 have not been mirrored. So we don't have a full mirror image of either altrose or glucose. We have only mirrored 2 out of the 4 chiral centers, so these are diastereoisomers, right? So in fact, all of the 16, we'll get there. But here, right, so we have D-altrose and D-glucose. Now, further from diastereoisomers, we have 2 specific types of diastereoisomers. We have ones in which we mirror only exactly 1 chiral center, okay? This is an epimer. So for example, glucose and mannose vary only at carbon 2. Carbons 3, 4, and 5 are all the same stereoscopic orientation, right? So we've only varied one of these. These are epimers. Anomers are something that not many people have encountered yet. Anomers are mirror images of each other. Well, mirror images of one specific chiral center, let's say. They are mirrors. They're specific types of epimers. They vary only at one position, but that position at which they vary in wasn't present before, right? So they vary in their stereochemistry at a new chiral center. And when does this happen? When can we just create a new chiral center? Well, here what we're looking at is the open chain form of glucose, right? But in solution, only about 1% of glucose exists in this open chain form. 99% of the glucose in solution actually exists in this closed chain form, right? So what happens is, and we'll see the mechanism for this closed chain closes in on itself, forms an intramolecular hemiacetal, and this creates a new chiral center here at this carbon number 1. So this carbon, which was not asymmetric, now becomes asymmetric. And we go from having 5 chiral carbons to 3, or rather 5 chiral carbons, right? This new chiral center here can have 2 different configurations, right? We can call it either alpha or beta, and we'll see how that is in just a minute. So anomers vary in the stereochemistry of their anomeric centers, or in this case, their anomeric carbons, the new chiral center that is formed through some process. Now, the number of diastereoisomers that can exist is simply 2 to the power of n, where n is the number of asymmetric carbons. So in the case of an aldohexose, like glucose, how many different diastereoisomers are there? Well, there's 4 chiral centers in glucose, so what's 2 to the power of 4? 16. So there are 16 possible aldohexoses, right? 8 of them will be the D configuration, and 8 of them will be the L configuration. What determines if a sugar is D or L is the position of the hydroxyl on the furthest chiral carbon away from either the aldehyde or ketone. In this case, here's our aldehyde at carbon number 1, so the furthest chiral carbon is carbon number 5. If the hydroxyl is on the right, that's a D sugar. If the hydroxyl is on the left in the Fischer projection, then that's an L sugar. So that's very easy to remember, L for left and then D for right. So here are our different aldoses. So again, here we have 8 aldohexoses: aldose, aldose, glucose, mannose, glucose, iose, galactose, and talose. Right? Notice that all that's happening, these are all just diastereomers of each other. Right? We're just varying on which side this hydroxyl is in the Fischer projection. Right? And we have 3 in this case, right? This one, this one, this one. The only thing that we're varying is the position of the hydroxyls on these 3. Right? Notice that carbon number 5 always has the hydroxyl on the right in all of these. These are all D stereoisomers. Okay? If we want the other 8 to make up the 16 that we just said before, well, all we have to do is to recreate this list, but make sure we put the hydroxyl on the left. Okay? So let's do an example here. Okay? If we wanted to draw L-glucose, so let's start with D-glucose. It's going to be what again? No. D-glucose, okay? So how would we draw then L-glucose? Well, we know it's still going to be an aldohexose, right? Or an aldohexose. So we'll start with our aldehyde group. We know it's still going to have 6 carbons. 1, 2, 3, 4, 5, 6. Carbon number 6 is going to be the same, so it's achiral, okay? So, how do we draw L-glucose? Well, let's start with carbon number 5 here. On which side should we put the hydroxyl in this case? Left. Okay, good. Carbon number 4 here. What side is the hydroxyl going to be on? On the right. Why do we think on the right? Remember, what's the relationship between L and D stereoisomers? They're enantiomers, right? Which means what? They're full mirror images of each other. And how do we take a full mirror image of a molecule?
You flip all of the carbons.
Right, so we have to flip all of the anomeric carbons. So in this case, carbon number 4 is asymmetric, so we have to flip that. Carbon number 3 is asymmetric, so we have to flip that. Carbon number 2 is asymmetric, so we have to flip that, right? Let's put all the hydrogens back. Here what we have is L-glucose. We've mirrored every possible asymmetric carbon, all right? So here we have D-glucose and L-glucose. What a lot of people will try to do is say, well, here's D-glucose, right? And you've heard, I already told you that if the OH is on the left, it's L. If the OH is on the right, it's D. So just flip that and call it a day, right? But that's not flipping the entire molecule. All we've done is to create an epimer. right? That is not the same thing as taking the enantiomer, which is the full mirror image. In other words, the mirror image of every possible asymmetric carbon. And we see the same thing with our pentoses up here, our aldopentoses, ribose, arabinose, xylose, and lysose. Here, notice, right, how many do we have? We have 4. Why? Because 2 to the power of, in this case, 3 asymmetric carbons is 8, and we're only looking at the 4 D isomers, so we have 4 further L isomers. The same thing here for erythros. We have 2 asymmetric carbons. 2 to the power of 2 is 4, right? And here we're only looking at 2 of those 4, 2 of the D enantiomers, right? And then of course glyceraldehyde, like we saw, right? So here we just have to double it and just flip the position of the hydroxyl. Same principle is true for the ketoses. They just have 1 less chiral center, right? Because carbon number 1 will always be symmetric in a ketose. Carbon number 2 in a ketose will always have the ketone group, right? So that leaves us with 1 fewer asymmetric carbons. So here, for example, the ketohexoses. Notice we only have 4 D versions, or 4 D enantiomers, and 4 L enantiomers for a total of 8, which is half of what we started with because we have 1 less chiral center in a ketose for a given number of carbons. So these are the most relevant sugars. These are the ones that you should definitely know. Ribose and deoxyribose, we've already examined from DNA and RNA. Glucose, mannose, galactose, and fructose, these are going to be important as we go on through metabolism, all right? Now, sugars, again, exist mainly in cyclic form, so this open chain form of the sugar is useful for identification, and as we'll see, is important for categorizing sugars that are either reducing or non-reducing, but they don't really exist in real life. At least the pentoses and hexoses don't, right? The septoses also, right? The tetroses and trioses, they do exist mainly in open chain form, but the pentoses, hexoses, and septoses exist in closed chain form. And the closed chains that they can form can be either 5-membered or 6-membered. Okay, so we can have either what we call a pyranose for its resemblance to the molecule purine, and furanose for its resemblance to the molecule furan. Now these are not sugars, okay, but they do resemble a sugar because they have an oxygen in their ring, which all cyclic sugars do. And how is it that sugars or carbohydrates can close the ring? In other words, how can we go from a open chain Fisher projection to a closed chain Hayward projection, as we'll see in just a minute? Well, this has to do with the fact that both aldehydes and ketones can react with alcohols to form either hemiacetals or hemiketyls, respectively. Right? So there's nothing that says that this has to happen between 2 different molecules. Instead, what we see in a sugar is that this happens intramolecularly. The alcohol in this case being one of the hydroxyls from the sugar, and the ketone or aldehyde being the ketone or aldehyde from the aldose or ketose. And when this happens, this hemiketyl and hemiacetal that forms links back to itself, closing a ring, forming again either a 6-membered pyranose or a 5-membered furanose. And we can see an example of that here with glucose. So here we have glucose in its open chain form. And what occurs is that the alcohol, in this case the hydroxyl, performs a nucleophilic attack on the aldehyde carbon, or the ketone carbon, depending, but in this case the aldehyde carbon. And when it does this, right, what happens is that these electrons from the double bond are pushed onto the oxygen because the alcohol and now this negatively charged oxygen are in close proximity. This oxygen attracts this hydrogen from the alcohol and becomes a hydroxyl. So we see that here, right? This H ends up on the hydroxyl on this oxygen, which was part of carbon number 1, or bound to carbon number 1, which is now here, right? So we've closed the ring. And from here, we can see why we can form 2 anomeric versions of, in this case, glucopyranose, the 6-membered ring. Depending on which side this hydroxyl attacks this carbon, whether it attacks from the top or it attacks from the bottom, that pushes the oxygen in the opposite direction. So if it attacks from the top, it pushes the oxygen to the bottom. If it attacks from the bottom, it pushes the oxygen to the top. And when the ring closes, now the position of that oxygen is locked in place, okay? So here now we have the hydroxyl on the same side as this carbon, the furthest carbon, carbon number 6, if the hydroxyl in the closed ring form is on the same side as the furthest carbon, we call that the beta anomer by convention. If the hydroxyl is on the opposite side as the furthest carbon, then by convention we call that the alpha anomer.
For the last slide, do we have to know the reaction mechanism?
This?
Yeah.
No. All right, so we have the alpha anomer and the beta anomer. Now, notice that all of these reactions are in equilibrium. And in fact, in solution, all three forms will exist in equilibrium. We'll have certain percent in the alpha, certain percent in the beta, and certain percent in the open chain form. We have all three going on at the same time. But which one predominates is based on, come back to that slide. Which one predominates is based on the slide here, steric hindrance. Okay? Notice that the ring that's formed, specifically the pyranose ring that's formed, is not aromatic, so it's not planar. And when we have a six-membered ring, we can adopt either the chair conformation or the boat conformation. Now, the boat conformation is going to be highly disfavored because a lot of these positions are too close to each other, so we'll never see a sugar in the boat configuration. What we will see is a sugar in the chair configuration, okay? So where we have the axial positions and the equatorial positions. What determines if the alpha anomer or the beta anomer will predominate in solution is the equatorial or axial position preferred. So if what we're looking at here, again, here's our oxygen, which used to be bound to this oxygen used to be the hydroxyl on carbon number 5, which is now in a covalent bond with carbon number 1, right? So here, carbon number 5, this up here, the equatorial position, this would be carbon number 6, okay? This over here, well, the axial and equatorial position depends on what carbon it is. But essentially, we want to put the hydroxyl so that it is farther away from all of the other groups, right? So in the case of glucose, right? Go back here. In the case of glucose, as it turns out, 2/3 of the glucose in solution will be in the beta configuration, and 2/3 or 1/3 of the glucose will be in alpha configuration. So 66% and 33%, with 1% of the glucose being in the open chain form. And we can see here how that looks in 3 dimensions. So here we have D-glucose. Right, so there's our oxygen. There we go. Okay, that's much better. All right, so here we have glucose, D-glucose specifically. Here, carbon number 1 is bound to the oxygen ring with carbon number 5, 4, 3, 2, and then back to 1. Here we have our hydroxyl, which used to be the double bond O in the aldehyde of glucose. Here we have all of the other hydroxyls. We'll get to how we determine if they're above or below the plane of the ring in just a second. And here we have carbon number 6, which is above the plane of the ring. So in this case, what do we have? Right? Well, here's carbon number 6, and here's the hydroxyl. So is this an alpha anomer or a beta anomer? Or is the hydroxyl on the same side or the opposite side as carbon number 6? It's on the same side, right? So this is beta glucose, right? Now, if we had alpha glucose, what would happen? Well, now we would switch the positions of this hydrogen and this hydroxyl. So this hydrogen would now be a hydroxyl, which puts it much closer to this hydroxyl. So that's less preferred than here, where it's just off in the middle of nowhere in the equatorial position, right? Now, how do we convert from the open chain form of a sugar to the closed chain form of a sugar? Okay? So there's a few rules that we can always follow. It makes it very easy to do this. The first thing we want to do is to draw our skeleton. Right? So are we drawing a pyranose or a pyranose? By convention, a pyranose is always drawn in this way, okay? With the oxygen in the top right corner. A pyranose is drawn with the oxygen at the top of the 5-membered ring. Just by convention, it makes it very easy. Also by convention, here, the anomeric carbon is going to be on the right, and the anomeric carbon will also be on the right. Okay, so now we know the numbers of our carbons. So let's number our carbons starting with the anomeric. So in the case of glucose, it would be carbon number 1, 2, 3, 4, 5, and 6 when we get to it. Is it alpha or beta? Right, if it's beta, then is the sugar D or L? Let's skip this step. If the sugar is D, the furthest carbon goes up. In this case, carbon number 6 would go up above the plane of the ring. If it's L, it goes down below the plane of the ring, and we'll see that is actually true in just a second here. Then is it alpha or beta? If it's alpha, then of course the hydroxyl is on the opposite side. If it's beta, then it's on the same side as carbon number 6, or whatever the furthest carbon happens to be. And then finally, all remaining carbons we can fill in. If the hydroxyl is on the left in the Fisher projection, then that carbon goes up in the Haworth projection. If the hydroxyl is on the right in the Fisher projection, then it goes down below the plane of the ring in the Haworth projection. All right, so here let's start with glucose. So let us number our carbons, 1, 2, 3, 4, 5. Is the sugar D or L? In this case, D glucose. So the carbon number 6 is going to be going up above the plane of the ring. Is it alpha or beta? So if we're drawing alpha, D glucose, now we put the hydroxyl on the opposite side as carbon number 6. And then finally we can fill in all the remaining carbons here. Carbon number 4 is to the right, so that goes down. Carbon number 3 is to the left, so that goes up. And carbon number 2 is to the right, so that goes down. And now we've completed our Haworth projection of alpha D glucopyranose. Okay, with here our anomeric carbon and carbon number 1. And the Haworth projection is such that these 3 bonds down here on the bottom are technically wedge bonds that are coming out at you. So this is as if you had the entire molecule tilted away from you with carbons 2 and 3 close and carbons 5 and the oxygen far away from you. So we can see that there's an actual above and below the plane of the ring. And we can see that this D and L business isn't just by convention, this is how the molecule actually looks. So again, here what we have is beta D glucopyranose. But if we look at L glucopyranose, all right, so let's position the oxygen in the top right corner, right? Here we have the oxygen in the top right corner, carbon number 1, 2, 3, 4, 5, and 6. So now we see that carbon number 6 is below the ring in the L enantiomer. Here we have the hydroxyl. This is the alpha configuration then of L glucose. So this is alpha L glucopyranose. Right? So again, just make sure you reorient yourself. So you have the oxygen in the top right corner, carbon number 1, the anomeric carbon 2, 3, 4, and so on. Okay? So here's again more practice. We can apply the same logic that we did to the to glucose, to basically any sugar to convert from the Haworth or from the Fisher projection to the Haworth projection and back. Right. So here again, if we want to make alpha D fructofuranose, and we know furanose, let's start with our skeleton here, with the oxygen at the top. We know this is going to be our anomeric carbon. In our case, the anomeric carbon is going to be carbon number 2. So we know carbon number 2 is going to have a hydroxyl connected to it in the Fisher projection, and carbon number 1, CH2OH, connected to it. So let's put that onto carbon number 2 here. Here, carbon number 1. Here's the hydroxyl, which was the ketone oxygen. We know that this is going to be D fructose. So we can't just by closing the ring. We can't just by closing the ring convert it from D to L. It's always going to be D now. That's what we're starting with. So because we're starting with D, we know that our closed ring will be D. So we'll put carbon number 6 above the plane of the ring, and that leaves us with carbon number 4, which is on the right. So that will be down, and carbon number 3, which is on the left. So that will be up. And now we have fructofuranose. So we talked about this, which exists, it's just steric hindrance. Which brings us to reducing sugars, right? So all simple sugars are what we call reducing sugars, meaning that they can act as reducing agents. And what does a reducing agent do? It reduces something else, and it itself gets oxidized. So in the case here of glucose, right, we can expose it to a special solution called Feeling solution. And Feeling solution has got a mix of chemicals that essentially just make copper 2+. And when we expose glucose to this feeling solution, right, well, copper 2+ is reduced to copper 1+. And in the process, glucose is oxidized to gluconic acid, right? Notice this up here, this aldehyde becomes a carboxylic acid, okay? So this carbon is oxidized while copper 2+ is reduced. And what this was used for originally was actually as a test for diabetes. If glucose is present, it will reduce copper 2+ to copper+, which then reacts with oxygen and forms a colored substrate. And this color could be measured. So if there was a lot of glucose in the urine, well, you can take a sample of urine from a patient and mix it with this feeling solution. If the color changed significantly, well, now you know that there was a high amount of glucose in the original sample, in other words, in the urine of the patient. So chances are they had diabetes. And as it turns out, any aldose can act as a reducing agent, right? So any aldose can act as a reducing agent, but only in the open chain form, because what we need is for there to be an aldehyde group here to act as the reducing agent, right? So how do we know if a sugar is a reducing sugar? Well, remember the closed chain form of any sugar is reversible with the open chain form of the sugar. So we need, even though we have 99% in the closed chain form, some of it will always, through equilibrium, be in this open chain form. Now, once this reacts with the copper, now we've reduced the concentration of the open chain form, which pushes this equilibrium forward. This is changed into gluconic acid, and so on and so on and so on. So after some amount of time, all of the sugar here will be, or most of the sugar will have been converted to gluconic acid, generating that pigmentation in the feeling solution, right? So it's a very effective test. Now, what about ketosis? Well, ketosis cannot undergo this reaction, but in feeling solution, there's actually a base component, and this base converts a ketose into an aldose so that it can act as a reducing agent. Not to mention that some ketoses, such as fructose, tautomerize naturally into an aldose at a low frequency, but it does happen. And when that happens, then it can react with copper 2+. So what do we need for a sugar to be a reducing sugar? Well, we need this process to take place. We need for the closed chain form to adopt the open chain form. And this can only happen if the anomeric carbon, which remember is pretty much the only thing that's changed, we need this anomeric carbon to remain unchanged. Which is to say, if now we took this carbon number 1 and we added a phosphate group, right? So instead of glucose, what we had was glucose 1-phosphate, where we replaced the OH with a phosphoryl group. Well, now that's a different compound, right? That's no longer glucose, that's glucose 1-phosphate. And that cannot adopt an aldehyde, obviously, because now there's no longer a hydroxyl on the anomeric carbon, right? So as long as there is a free hydroxyl, which is to say that the anomeric carbon has not been modified, this reverse process of ring opening is possible, and it can act as a reducing sugar. So we can modify the anomeric carbon in a couple of ways. We can modify the anomeric carbon by either adding, like we just went over, a phosphoryl group. We can modify that by linking the anomeric carbon to another sugar in a process we call glycosylation. We'll see that in just a second. But as long as there is an anomeric carbon, right, with a free hydroxyl, then we consider that sugar to be a reducing sugar. And this is important because it also lends polarity to polysaccharides, as we'll see. So here's the most common sugars in ring form. You should also know these off the top of your head, specifically glucose and fructose, and galactose. We're going to cover these in chapter 16, what happens to them. Now, glucose can bind to proteins. Okay, we'll see this in, well, I don't know if we'll get a chance to really go over it, but I do want to touch on it through a process called glycation. Sugars naturally can react with amines, alcohols, and phosphates. Okay, when they react with these amines, alcohols, or phosphates, we call that glycation. And where do we find a lot of amines in the cell is, of course, proteins. So on the ends of lysines, at the ends of asparagines, right, we find these amine groups, not to mention the N-terminus of the different chains of a protein. These can all react with glucose or other sugars when the concentration of those sugars is high enough, right? And this leads to one of the markers that is kind of followed for diabetes. Okay, so again, back to diabetes. If glucose concentrations are high, what's going to happen is that all of this excess glucose in the blood, well, what's else in the blood? Called erythrocytes, right? And what's inside of erythrocytes? Hemoglobin, right? And so, a lot of hemoglobin, mostly hemoglobin. So all this extra sugar is now in close proximity with all of this, hemoglobin in the erythrocytes. Specific lysines in this hemoglobin can be glycated, right? And after that glycation event, right, we can cross-link that sugar modification, in this case glucose, to the hemoglobin itself, which is to say that we form another covalent bond, not only between the sugar and the amine on lysine, but between the sugar and another part of hemoglobin. So now that sugar is really on there. And when we get that cross-linking event, what we end up with is something called an advanced glycation endpoint, or end product, an AGE. In the case of hemoglobin, that advanced glycation end product is called hemoglobin A1C. Recall that hemoglobin A is the adult isoform of hemoglobin. 1C, or 1C, is just designating that has been glycosylated. And when is it glycosylated? When there's a lot of sugar in the blood, as in untreated diabetes, right? Now, all of us have a certain amount of HbA1c in our blood. It's about 6%. Okay, but in untreated diabetes, if it's prolonged enough and the level of glucose is high enough for a long enough amount of time, well, now that 6% A1C starts to climb up and up and up to about 10% or higher. And because this event only takes place when concentration of glucose is high, and because now we've got hemoglobin bound to glucose, and that hemoglobin is quite stable, now we have a long-term measure of the average glucose levels in a person's blood, right? So if you take a finger prick of your blood and use it like on one of those at-home testers, well, that's going to tell you what your blood glucose level is right now. But if you measure your A1C levels, what you're doing is measuring what has been the effect of your overall glucose concentration in your blood over time, right? Has there been enough glucose present for a long enough amount of time in order to glycate enough hemoglobin so that we can measure an increased amount of HbA1c levels? So all of these drugs, right, like Jardiance that are talking about managing and lowering your A1C levels, there's nothing inherently wrong with HbA1c. It binds oxygen and behaves kinetically exactly the same as just HbA, right? But it's simply just a measure of how under control essentially your diabetes are. So they're helping to manage your A1C levels not because A1C is bad, but because that's indicative of your disease state.
Doesn't excess glucose get stored as glycogen?
Yes, it should, unless you're diabetic, right? So insulin, for example, in type 1 diabetes, where you don't produce insulin, or type 2 diabetes, where you're resistant to the effects of insulin. Insulin is what actually promotes the uptake of glucose from the blood, and it's only in the cell that glucose is stored as glycogen, which we'll see in chapter 21. Now, if you either don't produce insulin or can't react to insulin, well, now all of that glucose in the blood remains in the blood and can now react with the hemoglobin that's in the erythrocytes. That was good. That was a good question. All right, monosaccharides again can be linked to alcohols or amines. So here, for example, we see methyl glucose. We have adenosine monophosphate. So here we have again a nucleotide that we saw in chapter 1. Or in chapter whatever it was. Okay, so here we're seeing the anomeric carbon of ribose and an N-glycosidic bond with, in this case, adenosine. We have an O-glycosidic bond between a methyl group and the hydroxyl here of methyl glucose, so we can modify. We can also, of course, phosphorylate glucose, as we'll see in chapter 16, or phosphorylate sugars more generally, right? And this actually is quite important for metabolism. But the bond between the anomeric carbon and something else, again, either an amine alcohol or a phosphate group, okay, we call that a glycosidic bond. If you remember when we discussed the structure of nucleotides, we said that the sugar is held to the base via a beta N glycosidic bond, and now we can understand all of those different components. Beta, because this bond is now on the same side as the furthest carbon, in this case carbon number 5, so this is a beta glycosidic bond. It's an N-glycosidic bond because specifically it's a glycosidic bond between the anomeric carbon and a nitrogen as opposed to an O-glycosidic bond. And it's a glycosidic bond because it involves the anomeric carbon of a sugar, right? And this is how all of the nucleotides nucleotide sugars, either ribose or deoxyribose, are linked to their bases via a beta and glycosidic bond. Phosphorylated sugars are key in energy generation and biosynthesis. So here we have glucose 6-phosphate, dihydroxyacetone phosphate, glyceraldehyde 3-phosphate. Notice dihydroxyacetone, glyceraldehyde, and glucose are all just monosaccharides, but they're specifically phosphorylated monosaccharides. And this is important for several reasons in metabolism. First, it makes the sugars anionic, right? So it gives them always a negative charge, at least a 2-. And when we have a charged molecule, this charged molecule is virtually impenetrable to the phospholipid bilayer, to the plasma membrane. So by phosphorylating sugars in the cytoplasm, what occurs is that we essentially now trap that sugar in the cell, which is what most tissues want, except for the liver, which we'll talk about later in the semester, right? So when a cell or a tissue imports glucose or whatever sugar, it is now selfish. It wants to keep that glucose so that it can use it for energy. The best way to do that is to trap it by phosphorylating it. And this is the first step, actually, taking a free glucose and phosphorylating it to form glucose 6-phosphate. This is the very first step in carbohydrate metabolism, like we'll see in chapter 16. Dihydroxyacetone phosphate and glyceraldehyde 3-phosphate are high energy intermediates in the glycolytic pathway, right? So here, we're not using phosphorylation to trap these molecules. Instead, we're using phosphorylation to add free energy to these molecules, to drive glycolysis forward, right? So phosphorylation is key for several reasons in metabolism. Now, monosaccharides can also be linked together to form polysaccharides. In this case, what we're seeing is specifically a disaccharide. What's important is that they're linked by a glycosidic bond, which always involves the anomeric carbon of at least one of the sugars, right? So in this case, we have 2 glucose molecules linked together by a glycosidic bond between carbons number 1 and 4. Of course, carbon number 1 here being the anomeric carbon. So what we call this is a 1,4 glycosidic bond. And further, we categorize it as alpha or beta depending on the configuration of the anomeric carbon involved in that bond. Okay, so in this case, we have only 1 anomeric carbon involved, and this is in the alpha configuration because this, what used to be a hydroxyl, was on the opposite side as carbon number 6. So this is specifically an alpha 1,4 glycosidic bond, made up of 2 glucose residues. The reason we call them residues is notice what we're missing. We're missing an OH from over here, and we're missing an OH from over here. So what we've lost is a water, okay? So this is the result of a condensation reaction, just like the addition of an amino acid was to a protein. And that's why we call those amino acids residues in the context of a polypeptide. We also call sugars residues in the context of a polysaccharide. And here specifically this disaccharide is called maltose. All right, now sucrose, lactose, and maltose are the most common disaccharides. Right? So let's look at lactose and maltose first. So we saw maltose before. It's made up of 2 glucose residues linked alpha 1,4, and we can name them systematically. This is the first example where we see that there's a common name and a systematic name. I wish everything just followed the systematic name, but of course all of these sugars were discovered at different times and then were named for different properties. You know, they turned a certain solution a certain color, or they're found in a certain type of wheat, right? So for example, maltose, that's where we get malt shakes from, or malt from beer brewing, right? Because they contain a lot of this specific sugar, which is made up of 2 glucose residues. So we can name them more systematically. We say alpha D glucopyronosyl is describing the first sugar. 1,4, because it's linked 1,4 from carbon number 1 to carbon number 4 to alpha D glucopyranose. So now we know the entire structure, but it's referred to as maltose, right? Lactose, same thing. Here we have a galactose and a glucose. So what we call this is beta D galactopyronosyl. So it's beta because this, what used to be the hydroxyl, is on the same side as carbon number 6. So this is beta D galactopyronosyl 1,4 alpha D glucopyranose. This is lactose, is what we find in milk. Okay. Now notice in both of these we have a polarity. Okay, we have one sugar that is now no longer a reducing sugar. Right? This sugar over here, this galactose, is no longer a reducing sugar because its anomeric carbon has been modified. It's now in a glycosidic bond, so it cannot open back up to form an aldehyde, so it can't reduce that feeling solution. This, however, glucose does have a free anomeric carbon, so it can open back up and form an aldehyde. Granted, carbon number 4 is now no longer going to be linked to a hydroxyl, it's going to be linked to a galactose, but that doesn't matter. All we need is that aldehyde a reducing agent. So now we have a non-reducing side and a reducing side. So similar to how DNA has a polarity going from 5' to 3', proteins have a polarity going from the N terminus to the C terminus, polysaccharides have a polarity going from the non-reducing side to the reducing side, right? Unless we have something like sucrose, right? Sucrose is an exception. Well, not really an exception, just an example of a non-reducing sugar. And why do we say that sucrose is a non-reducing sugar? Well, let's look at the structure. Here we have alpha-D-glucopyranosyl, 1,2-beta-defuranose. And remember, in glucose, carbon number 1 is the anomeric carbon. Fructose is a ketose, meaning that carbon number 2 will be the anomeric carbon. And in this case, we're linking carbons number 1 to carbon number 2. Both anomeric carbons in this disaccharide have been modified. So neither the glucose on the left or the fructose on the right can open back up to form either an aldose or a ketose. So neither of them can act as a reducing agent. So sucrose is an example of a non-reducing sugar. And there are many examples of non-reducing sugars. Okay, but sucrose is the most common. This is just table sugar, right? Now, in order to digest these, by the way, right, our bodies are only capable of digesting simple monosaccharides, so galactose and fructose and glucose, right? So all these disaccharides and polysaccharides from, for example, starches, right, they have to first be broken down by digestive enzymes. They have to be hydrolyzed apart. So before maltose can be used for digestion or metabolism in our bodies, it first has to be hydrolyzed into one glucopyranose and another glucopyranose. And the same for lactose and the same for sucrose. Sucrose has to be hydrolyzed into a glucose and fructose, which our bodies are more than happy to accommodate. Now, this gets a little bit more, well, not more complex, but just more involved when we look into storage forms of glucose. This is how we get most of our glucose throughout the day. It's not just, sucrose, table sugar. Most people don't eat that much table sugar, but there is a lot of sugar in, for example, tubers, certain types of vegetables. So what are storage forms of glucose? Well, if we consider that a cell needs a certain amount of glucose in order to just carry out its basal metabolism, well, that amount of glucose is actually prohibitive. The concentration of glucose in the cell would be astronomical in order to hold on to that much glucose. There would be many, many glucose molecules. And when this happens, if we remember from Gen Chem, what is the osmotic pressure? Well, osmotic pressure is dependent only on the number of molecules. Right? So if we have millions or billions of glucose molecules in a cell, in order to relieve that osmotic imbalance, now water will rush into the cell through osmosis. And because the cell membrane is mostly permeable to water, right? So what's going to happen now? Well, the cell will start to swell and to swell and to swell until eventually it bursts, okay? In order to combat this, right, well, the cell still needs that much glucose, but instead of storing it as individual glucose molecules, they polymerize it into one giant glucose molecule called glycogen, right? And in this case now, because again, that osmotic pressure is based only on the number of molecules, we've taken millions of molecules and combine them into one bigger molecule, but that doesn't matter. Now we've relieved the osmotic pressure. This is why we need storage forms of glucose like glycogen and starch. So in animals, the storage form of glucose is again that glycogen, and glycogen has a very interesting topology. It's a branched polysaccharide made up of thousands or tens of thousands of glucose residues. The main chain of a glycogen molecule is made up of glucose residues linked in an alpha-1,4 configuration, so similar to maltose. Here, right, we have an alpha-1,4 linkage. We can take this anomeric carbon and link it to carbon number 4 of another glucose, which will have a free anomeric carbon, carbon number 1, which we can add to another carbon 4 of another glucose molecule, and so on and so on. So we have many hundreds or thousands of glucose residues linked alpha-1,4, forming a linear chain, right? Now the topology is linear, but as we'll see in just a second, the three-dimensional structure is actually curved and it forms these tubes. But for now, just note, right, the topology is linear, alpha-1,4. Every 10 to 12 glucose residues in this chain, right, will have, of course, a glucose that is linked both alpha-1,4 and alpha-1,4, because it's in the middle of the chain, but every 10 to 12 residues, there will be one that is also linked alpha-1,6, as we see over here. This we call a branch point, because this glucose up here now serves as the end, or beginning, I should say, of a new glucose chain that are all linked alpha 1,4. So the topology looks like this, right? We have a bunch of glucose residues in a chain linked alpha 1,4. Right, so we have carbon number 1 to carbon number 4. And we have carbon number 1 of this one to carbon number 4 of the next one. Every so often we'll get a 1,6, which is linked to carbon number 1 of a glucose. This carbon number 4 of this glucose over here can be linked to carbon number 1 of another glucose over here. And so on. Every 10 to 12 over here we'll get another branch, so we can have a branch point on a branch. So we have branches on branches on branches, every 10 to 12 residues. And if you notice over here, what do we have? On the terminal glucose, we have a terminal hydroxyl. And on all of these over here, well, the anomeric carbon is always participating in a glycosidic bond, either alpha 1,4 or alpha 1,6. So we only have one anomeric carbon here, which means that glycogen, no matter how many branch points we have, only will have one anomeric carbon. Meaning it's got one reducing end, or one free anomeric carbon, I should say. So it's got a reducing end all the way at the beginning. All of the ends of the branches, right, over here and over here and over here where there's more, right, so these always end in carbon number 4, these would be non-reducing ends. And they can have many thousands of non-reducing ends. In fact, the number of non-reducing ends is equal to the number of branch points plus 1. Right, so we have 5 branch points, we have 6 non-reducing ends. And it's at these non-reducing ends that all of the chemistry involving glycogen occurs, which is very useful because that means that we can have many parallel metabolic reactions occurring on the same glycogen molecule at the same time, which we'll talk about in chapter 21. Now, starches, which are the main storage forms of glucose in plants, come in 2 flavors, right? We have amylose and amylopectin. Amylose is very easy to understand. This is strictly a linear polymer, topologically speaking, meaning that they're all sugar residues, or glucose residues specifically, linked alpha 1,4. Amylopectin is almost identical to glycogen in that it's alpha 1,4 linked glucose with alpha 1,6 branches, except that the extent of the branching is much reduced in amylopectin. It only branches every 20 to 30 glucose residues as opposed to the 10 to 12 glucose residues that we find in glycogen. Now, in addition to storage forms, glucose can also, or polysaccharides can also serve structural purposes, right? So here we have starch and glycogen, which are all linked alpha 1,4 together. Remember, I told you that topologically speaking, these alpha 1,4 linked glucose molecules are linear, but three-dimensionally they're curved, right? And they form this kind of spiral, which ends up looking like a hollow cylinder, right? And these are very useful in order to digest or synthesize a lot of this glycogen and starch, which is what those are meant for. However, if we instead link those glucose residues together beta 1,4, right, as opposed to alpha 1,4, what we end up is a polymer that is linear both topologically and three-dimensionally, right? And we call this cellulose. Cellulose and amylose are chemically identical. The only thing different between them is that the glucose residues in cellulose are linked beta 1,4 and the glucose residues in amylose are linked alpha 1,4. And because these are beta 1,4 linkages, this gives this a linear three-dimensional structure, which means that we can have polymers of cellulose hydrogen bonding with other polymers of cellulose, which are hydrogen bonding with other polymers of cellulose. And we have to remember that these cellulose polymers can be thousands of glucose residues long, so we're forming many, many thousands of hydrogen bonds. And overall, all these hydrogen bonds add up to be very strong. So where do we find cellulose? We find these in woods, we find them in the stems of plants, because all these hydrogen bonds between the cellulose polymers are acting together in order to give rigidity, right? All right, so glycosylation can act as a nutrient sensor. So as we talked about with hemoglobin A1C, proteins can be modified with sugars, either non-enzymatically, as it was with A1C, or enzymatically. But importantly, right, a lot of times these sugar modifications on these proteins can act as nutrient sensors. Because sugars can be modified, remember we can add amines, we can add phosphates, right? And we can modify sugars in such a way that they serve a more interesting purpose, right? So glycosylate can act as a nutrient sensor. What we're looking at here is N-acetylglucosamine, right? So let's break that name down. Glucosamine is a glucose amine, so it's an amine sugar. It's an amine derivative of glucose, and you can see that here. So let's ignore this acetyl group. What we have here is just glucosamine, glucose amine. This would be an NH2. This would signal both the availability of glucose, in other words, carbohydrates, and it will also signal the availability of nitrogen, which corresponds to the availability of proteins for metabolism. Now we can add onto the amine an acetyl group, which is going to signal the availability of fatty acids. You'll see in chapter 22, the oxidation of fatty acids results in a molecule called acetyl coenzyme A. And that acetyl coenzyme A in excess can contribute acetyl groups to glucosamine, leaving us with N-acetylglucosamine. This modification here can serve as a signal to certain enzymes, right? So for example, if there's a glycosyl transferase that will transfer an N-acetylglucosamine onto some metabolic enzyme, well, maybe that'll turn on that metabolic enzyme because now it knows that there's the presence of carbohydrates, fatty acids, and protein. So it can do something, right? So glycosylation can act as a nutrient sensor. Now carbohydrates, right, like that N-acetylglucosamine, can be linked to proteins in three categories: glycoproteins, proteoglycans, and mucins. I don't think we'll get to proteoglycans, but I do want to try to talk a little bit about glycoproteins. Glycoproteins are mostly protein by weight, so this is similar to protein phosphorylation. And protein phosphorylation is used to modify a protein, but you can still recognize it as mostly a protein that has been modified in some way. The same is true for a glycoprotein. It's mostly a protein that has been modified in some way with a sugar, either, for example, N-acetylglucosamine or N-acetylgalactosamine, and they can be linked to a protein via either an O linkage on a serine or threonine. Recall that those end in a hydroxyl, so an alcohol, and they can be linked onto a sugar, or through an N linkage at the end of an asparagine. Right? So here we have is an N-acetylglucosamine linked to an asparagine residue by an N-glycosidic bond. Notice here we're involving the anomeric carbon, that's a must. And here we have is an O linkage to the terminal hydroxyl of a serine residue of the protein. Right? Notice again, this is an O-glycosidic bond, we're involving the anomeric carbon, which is also required. Now, modification of a protein doesn't stop there. It's not as simple as phosphorylation, where you just add a phosphoryl group and call it a day. Right? Phosphorylation, or rather glycosylation, is always more complex, and it always involves these core 5 sugars here. Right? It involves 2 N-acetylglucosamines and 3 mannoses. This pentasaccharide core is present in all at least N-linked glycosylation events. From here, now we can add more sugars onto this core, right? And it's this pattern of the sugars that helps to communicate something about that protein. So when we find a lot of glycosylation are on proteins that are secreted, right? It helps to identify that protein to its target and so on. In fact, this pattern of glycosylation, right? Not these 2 specifically, these are just 2 examples, but the pattern of glycosylation on a protein is kind of the third genetic language that isn't really understood right now. Right? So we know the genetic language of DNA and RNA, we know the genetic language of proteins. Now there's a whole third genetic language that is still being identified. We don't know yet what the pattern of glycosylation on a given protein means, but we know that it's important because in fact changes in the pattern of glycosylation can lead to diseases like eye-cell disease or disorders of glycosylation, which can be very disastrous, very severe, like eye-cell disease. So we know that the pattern of glycosylation, and that's due to that eye-cell disease, due to the just 1 mannose residue being incorrectly added to a specific protein that is destined for the proteasome. We won't get into the details, but even a difference of 1 sugar on a sugar modification can lead to disease states. So clearly it's very important. We just don't understand it yet. Right? So there's a whole different language, the sugar code. Here, for example, we have this erythropoietin, which is modified at 3 asparagines via N linkages and at 1 serine. So we can see that the pattern of glycosylation varies between first N and O links. So here again, all the N links have the same pentasaccharide core, those 2 acetylglucosamines and 3 mannoses. But the pattern also tells you something about the individual. Different individuals can glycosylate their proteins in different patterns, and the rest of our body is set up to recognize those. In fact, erythropoietin, which is the hormone that stimulates the growth of erythrocytes, okay, can be synthesized chemically. Right, so we're very good at recombinant DNA techniques, right? So we can synthesize and express erythropoietin. And endurance athletes, like for the Tour de France and stuff, they dope their blood with extra erythropoietin, right, in order to increase the amount of erythrocytes, increase the amount of hemoglobin, so increase the oxygen carrying capacity, and increase their endurance, which of course is needed for the Tour de France, right? But that can be easily detected, right, and why? Well, these glycosylation events on erythropoietin are specific to the individual and are difficult to replicate. Okay? They stabilize erythropoietin in the blood, so in the absence of these glycosylation events, this is quickly degraded. So this synthetic erythropoietin has to be glycosylated. But because it's so difficult to do, right, they all look the same, which isn't how erythropoietin would normally look. So I'll leave it there, and we're not going to talk about proteoglycans or mutants. So proteoglycans we can do on the exam. We'll stop here with glycoproteins. Remember the exam's on Tuesday. I'm going to have